Temperatures swing from near absolute zero to millions of degrees within the same cubic light year. Radiation that would shred your DNA pours in from every direction without anything to stop it. 2 human-made spacecraft have crossed into this abyss, and what they found rewrote everything we thought we knew about the space between stars. This is not the gentle darkness of science fiction. This is interstellar space, and its true nature is far more terrifying than silence. If you enjoy journeys that change how you see reality, consider tapping that like button and subscribe. Now, settle in, get comfortable, let's begin. The sun is doing something right now that most people never consider. It is screaming into the void, not with sound, because sound cannot propagate through vacuum, but with matter. Every single second, our star ejects roughly 1 million tons of charged particles outward in every direction at speeds exceeding 1 million miles per hour. Protons, electrons, and helium nuclei stream away from the solar surface in a torrent so violent that it strips paint-thick layers of atmosphere from any unshielded body in its path. This relentless outpouring of material is called the solar wind, and it has been blowing continuously for roughly 4.5 billion years, ever since our star ignited and began fusing hydrogen in its core. But the solar wind does not simply scatter into infinity and vanish. It does something far more important. It inflates a structure, a vast, dynamic, invisible bubble of magnetized plasma that surrounds our entire solar system and pushes outward against the pressure of the galaxy itself. Scientists call this structure the heliosphere. Most people have never heard the word, yet it may be the single most consequential boundary in their lives, the difference between an environment that supports life and one that would slowly destroy it. The heliosphere is the sun's domain. Everything inside it is shaped, governed, and protected by our star's magnetic field and particle output. The magnetic field lines that originate at the solar surface are carried outward by the solar wind, twisting into an enormous spiral pattern that astronomers call the Parker spiral, named after the physicist Eugene Parker, who first predicted the solar wind's existence in 1958. At the time, Parker's proposal was controversial. Many physicists dismissed the idea that the sun could continuously emit a stream of charged particles fast enough to reach the outer solar system. He submitted his paper to the Astrophysical Journal, where both reviewers recommended rejection. The editor overruled them and published it anyway. Within a few years, direct spacecraft measurements confirmed that Parker was right. The solar wind was real, and it was everywhere. Those magnetic field lines, carried outward by the wind, wrap around the sun's equatorial plane and extend outward for billions of miles, creating a magnetic architecture that defines the local space environment. Inside this architecture, conditions are fundamentally different from what lies beyond. The particle population is dominated by solar material. Protons and electrons from the sun vastly outnumber particles originating elsewhere. The magnetic field traces back to a single source, our star, giving the entire region a coherent magnetic identity. And critically, the heliosphere acts as a shield against one of the most persistent threats in the galaxy: galactic cosmic rays. High-energy particles, primarily protons but also heavier nuclei, that have been accelerated to extraordinary speeds by supernova shock waves and other violent processes scattered throughout the Milky Way. They stream through the galaxy in every direction, carrying energies that can shatter atomic nuclei and damage molecular bonds in biological tissue. Without the heliosphere, they would bombard the inner solar system with significantly greater intensity than what we experience on Earth. Estimates from NASA and the European Space Agency suggest that the heliosphere reduces the galactic cosmic ray flux reaching the inner solar system by roughly 30 to 50% during periods of elevated solar activity, and by a smaller but still meaningful margin during solar minimum. This shielding is not perfect. The highest energy cosmic rays punch through regardless, but the reduction is significant enough that removing it entirely would measurably alter the radiation environment on Earth's surface, with potential consequences for atmospheric chemistry, mutation rates, and biological exposure over geological timescales. Every human civilization that has ever existed flourished inside this bubble. Every spacecraft ever launched remained within it, with exactly 2 exceptions. Every planet, moon, asteroid, and comet we have ever studied with close-range instruments orbits inside the heliosphere's protective embrace. The bubble is our cosmic shelter, inflated and maintained by the tireless nuclear furnace at the center of our planetary system. But all shelters have walls, and all walls have an outside. The heliosphere does not end abruptly. It transitions through a series of distinct layers, each marking a different phase in the interaction between the outward-pushing solar wind and the inward-pressing interstellar medium. Understanding these layers is essential to grasping where interstellar space truly begins and why crossing that threshold changes everything. The outermost region, still clearly dominated by fast-moving solar wind, extends from the Sun outward to a boundary called the termination shock. Throughout this vast inner zone, the solar wind races outward at supersonic speeds, typically between 300 and 800 kilometers per second, depending on solar conditions and latitude. The wind is thin by any terrestrial standard, only a few particles per cubic centimeter even near Earth, but it moves with tremendous velocity and carries the Sun's magnetic field with it, maintaining the heliosphere's structure through sheer kinetic pressure. The termination shock is the first major structural boundary. It marks the distance from the Sun, where the solar wind can no longer maintain supersonic speed against the mounting pressure of the interstellar medium pressing inward. At this point, the wind undergoes a dramatic deceleration, dropping from supersonic to subsonic velocity in a relatively narrow transition zone. The physics is analogous to a sonic boom in reverse. When a jet aircraft exceeds the speed of sound, it creates a shockwave. When the solar wind drops below the equivalent of the local sound speed in the heliospheric plasma, a similar shock structure forms, except this one is spheroidal and wraps around the entire solar system. Voyager 1 crossed the termination shock in December of 2004, at a distance of approximately 94 astronomical units from the Sun. 1 astronomical unit equals the mean distance from Earth to the Sun, about 93 million miles. So Voyager 1 encountered this boundary roughly 8.7 billion miles from home. The crossing was not clean and simple. The spacecraft's instruments recorded multiple shock-like signatures over a period of days, suggesting it crossed and recrossed the boundary as the termination shock rippled back and forth in response to fluctuations in solar wind pressure. The boundary was alive, breathing, flexing in real time as the Sun's output varied. Voyager 2 crossed the termination shock 3 years later, in August of 2007, but at a noticeably different distance, approximately 84 astronomical units. The 10 astronomical unit discrepancy between the two crossings, roughly a billion miles, revealed something important about the heliosphere's geometry. It is not a perfect sphere. The interstellar medium through which the solar system moves exerts greater pressure on the leading edge of the heliosphere, compressing it, while the trailing edge stretches outward into a long tail. The heliosphere is shaped more like a windsock than a soap bubble, deformed by its motion through the local interstellar environment at roughly 26 kilometers per second. What the Voyager instruments recorded at the termination shock confirmed theoretical predictions in some respects and defied them in others. The expected deceleration occurred. Solar wind speed dropped sharply, but the plasma temperature spiked far higher than models anticipated, suggesting that the conversion of kinetic energy into thermal energy at the shock was more efficient than expected. The magnetic field exhibited turbulent fluctuations, indicating the termination shock region was far more dynamic and chaotic than the smooth, clean boundary theorists had envisioned. The real heliosphere, as is so often the case in science, turned out to be messier and more interesting than the model. Beyond the termination shock lies the heliosheath, a thick, turbulent buffer zone where the decelerated solar wind piles up, heats, and churns. If the termination shock is the point where the solar wind slams on the brakes, the heliosheath is the resulting traffic jam. Solar particles in this region no longer race outward in a coherent flow. They slow, compress, heat to millions of degrees, and flow sideways along the inner boundary of the heliosphere, gradually being redirected toward the tail of the bubble, a structure called the heliotail that streams away from the Sun in the direction opposite to our star's motion through the galaxy. The heliosheath is a strange and violent place by the standards of interplanetary space. Magnetic fields become tangled and disordered, losing the clean spiral pattern that characterizes the inner heliosphere. The plasma is choppy, unpredictable, and structured in ways that surprised scientists when the first direct measurements arrived. Voyager 1 spent nearly 9 years traversing this region. From late 2004 to mid-2012, traveling through conditions that no human-made instrument had ever sampled before. During that crossing, both Voyager spacecraft detected something no model had clearly predicted. Regions of enhanced magnetic field strength appeared as discrete structures within the heliosheath, magnetic bubbles roughly 1 astronomical unit across, that formed through instabilities in the turbulent plasma. Scientists described these as a foam of magnetic islands, a frothy zone where the sun's magnetic field had broken into a chaotic jumble of discrete cells rather than maintaining any large-scale coherent structure. The heliosheath was not the smooth, gradually changing zone that simple models predicted. It was structured, dynamic, and far more complex than anyone had anticipated from the comfort of theoretical calculations made on Earth. During the long years within the heliosheath, Voyager 1's instruments also tracked the slow evolution of 2 critical measurements. The density of solar origin particles, which had been declining steadily, continued its downward trend. Simultaneously, the flux of galactic cosmic rays, which had been gradually increasing throughout the outer heliosphere, continued to climb. These 2 trends were converging toward a crossover point, a location where solar particles would give way entirely to galactic particles, where the sun's influence would finally be replaced by the galaxies. The scientists monitoring the data from their offices at the Jet Propulsion Laboratory knew that crossover point had a name: the heliopause, and then it came. The heliopause is the outermost edge of the heliosphere, the surface where the outward pressure of the solar wind finally reaches equilibrium with the inward pressure of the interstellar medium. Cross this line, and you are no longer inside the sun's magnetic domain. You are no longer surrounded by particles that originated at our star. You have entered a region governed by galactic conditions, where the local interstellar magnetic field replaces the solar magnetic field, where interstellar plasma replaces solar wind plasma, and where galactic cosmic rays arrive undiminished by any solar shielding. Voyager 1 crossed the heliopause on or around August 25, 2012, at a distance of approximately 121 astronomical units from the Sun. That translates to roughly 11.3 billion miles. The crossing was not immediately recognized. Data from the spacecraft arrived on Earth with a lag of approximately 17 hours at the speed of light, and the instruments told a story that required months of careful, sometimes contentious analysis to fully interpret. The confusion arose because different instruments gave seemingly contradictory signals. The cosmic ray detector told a clear story. On August 25th, the count rate of galactic cosmic rays jumped sharply upward, roughly 9% above the already elevated levels measured in the outer heliosheath, and substantially higher than values recorded deeper inside the heliosphere, and the flux of lower energy solar particles dropped to essentially 0. These 2 signatures together painted an unambiguous picture. The spacecraft had left the zone dominated by solar particles and entered the zone dominated by galactic particles. But the magnetometer told a different story, or seemed to. Many models had predicted that the magnetic field direction would rotate substantially at the heliopause, shifting from the Sun's Parker spiral orientation to the interstellar field's orientation. Voyager 1's magnetometer recorded a change in field strength and some shift in direction, but not the dramatic rotation that some theorists expected. This discrepancy fueled months of debate. Had Voyager 1 truly crossed the heliopause, or had it merely entered an unusual region within the heliosheath where solar particles happened to be depleted? The resolution came from an unexpected source. In early 2012, a powerful solar eruption sent a shockwave rippling outward through the heliosphere. Approximately 13 months later, in April of 2013, the disturbance reached Voyager 1's location and caused the thin plasma surrounding the spacecraft to oscillate, producing measurable electron density waves. The plasma wave instrument aboard Voyager 1 detected these oscillations, and crucially, their frequency allowed scientists to calculate the density of the surrounding plasma directly. The density was approximately 0.055 electrons per cubic centimeter, far higher than what would be expected inside the heliosheath, and consistent with the expected density of the local interstellar medium. This measurement settled the debate. Voyager 1 was not in a depleted pocket of the heliosheath. It was in interstellar space. The plasma density confirmed it. The cosmic ray data confirmed it. The only remaining puzzle was why the magnetic field direction had not shifted more dramatically, and subsequent analysis suggested that the interstellar field in our immediate neighborhood happens to be oriented not too differently from the outer heliospheric field, a coincidence of local geometry rather than evidence against the crossing. Voyager 2 provided even more definitive confirmation when it crossed the heliopause on November 5, 2018, at a distance of approximately 119 astronomical units. Crucially, Voyager 2 carried a functioning plasma science instrument, a device that directly measures the temperature, density, and velocity of the surrounding charged particles. Voyager 1's equivalent instrument had failed in 1980, decades before the heliopause crossing, robbing scientists of the most direct measurement possible for that historic first passage. Voyager 2's plasma instrument delivered beautifully. The data showed a sharp, unambiguous transition. Inside the heliosheath, the plasma was hot, roughly 30,000 to 50,000 Kelvin, and composed predominantly of solar wind protons and electrons flowing outward at reduced speeds. Outside, the plasma temperature dropped, the density increased, and the composition shifted to interstellar material, primarily neutral and ionized hydrogen, originating not from the Sun, but from the broader galactic environment. The change occurred over a remarkably thin boundary, less than 1 astronomical unit in extent. The heliosphere did not fade out gradually. It ended. The transition was a membrane, not a gradient. This sharpness deserves emphasis because it overturns a common misconception. Many people imagine the boundary of the heliosphere as a gradual dimming, a long, slow transition from solar to interstellar conditions unfolding over billions of miles. The Voyager data showed the opposite. The heliopause is thin, the change is crisp. On one side, the Sun rules. On the other, the galaxy takes over. The contrast is stark, measured in different particle populations, different magnetic field configurations, different radiation environments, and it happens within a distance smaller than the gap between Earth and the Sun. Here is where a critical distinction must be made, because it addresses one of the most common misunderstandings about where interstellar space actually begins. When most people hear the term solar system, they think of the Sun and its family of planets, moons, asteroids, and comets. The outermost recognized planet, Neptune, orbits at roughly 30 astronomical units. The Kuiper Belt, home to Pluto and thousands of icy bodies, extends to approximately 50 astronomical units. Beyond that, astronomers believe, lies the Oort cloud, a hypothetical shell of icy objects that may stretch from roughly 2,000 to as far as 100,000 astronomical units from the Sun. Objects in the Oort cloud are still gravitationally bound to our star. They orbit the Sun over periods of millions of years, nudged by the faint gravitational influence of passing stars and the slow tidal pull of the Milky Way itself. This means the solar system, defined gravitationally, extends enormously far, possibly 1 to 2 light-years from the Sun in every direction. The heliopause, by contrast, sits at roughly 120 to 140 astronomical units. That is less than 2/100ths of a light-year. The heliosphere occupies a tiny fraction of the Sun's gravitational domain, less than 1/10,000th of the volume enclosed by the Oort cloud's outer boundary. This creates a situation that is both physically real and deeply haunting. Objects in the outer Oort cloud are still part of our solar system in the gravitational sense. They still orbit the Sun, but they exist outside the heliosphere, fully immersed in interstellar space. They have no solar magnetic shielding. They are bombarded by the full galactic cosmic ray flux. They drift through interstellar plasma. They are, for all practical environmental purposes, interstellar objects that happen to be gravitationally tethered to a distant star. Their surfaces have been processed by galactic cosmic radiation for billions of years. Their chemical evolution has been shaped by the interstellar medium rather than by the solar wind. They are members of the solar system in name, but residents of interstellar space in reality. Interstellar space, therefore, does not begin at the edge of the solar system's gravitational influence. It begins much closer, at the heliopause, and everything beyond that thin membrane exists in a fundamentally different physical environment, regardless of whether it is still gravitationally attached to the Sun. This distinction matters because it reveals the true nature of the heliopause as a survival boundary rather than an abstract demarcation. The gravitational boundary of the solar system is an imaginary surface where the Sun's pull becomes weaker than a neighbouring star's pull. Nothing physically changes when you cross it. You do not feel it. Your instruments do not register it. It is a mathematical concept, not a physical event. But the heliopause is a real, measurable transition. The magnetic environment transforms. The particle population shifts. The radiation exposure changes. The energy landscape alters. An object crossing the heliopause undergoes a genuine instrument-detectable transformation in its physical circumstances. An object crossing the gravitational boundary notices nothing at all. This is why the Voyager crossings were so scientifically momentous. They were not symbolic milestones or arbitrary lines drawn on a map. They were direct measurements of a real physical transition, the first time any human-built instrument had tasted the interstellar medium and reported back on what it found. What it found was sobering. Beyond the heliopause, the environment reported by both spacecraft confirmed decades of theoretical predictions in their broad strokes, while revealing unexpected complexity in the details. The interstellar plasma was denser than the depleted solar wind at the heliosphere's edge, approximately 0.05 to 0.1 particles per cubic centimetre. The galactic magnetic field was present and oriented roughly as models had predicted, though with fine-scale variations suggesting local turbulence and structure. And the cosmic ray intensity increased to a steady, elevated plateau that showed no sign of decreasing with further distance from the Sun. That last detail carries profound implications. Inside the heliosphere, cosmic ray intensity varies with the solar cycle. When the Sun is active, its stronger magnetic field and denser solar wind more effectively deflect incoming cosmic rays, reducing the flux at Earth. When the Sun is quiet, more cosmic rays penetrate. This variability means the radiation environment inside the bubble is modulated, partially controlled by our star's rhythmic output. Outside the heliopause, that modulation disappears. The cosmic ray flux measured by Voyager 1 after its crossing has remained essentially constant, varying only in response to occasional heliospheric disturbances, propagating outward past the heliopause like ripples from a stone dropped in a pond. The background level is simply the galactic average for our neighbourhood, and it is relentless. There is no quiet period, there is no enhanced shielding phase. The radiation arrives continuously, from every direction, at every moment, without variation and without mercy. It is the steady-state condition of the galaxy, and anything outside a star's protective bubble is exposed to it in full. Voyager 1 and Voyager 2 continue transmitting from this realm as of the mid-2020s, though their power reserves are dwindling steadily. Each spacecraft carries a radioisotope thermoelectric generator fueled by the radioactive decay of plutonium-238. These generators lose approximately 4 watts of electrical output per year as the plutonium decays and the thermoelectric junctions degrade. Scientists at the Jet Propulsion Laboratory have been systematically shutting down instruments to conserve the remaining power for priority measurements. The heaters that protect instruments from the cold of deep space have been turned off one by one. Instruments that still function share power in shifts. The engineering team has performed what amounts to electronic triage, deciding which measurements are worth preserving as the power budget shrinks towards zero. By the mid-2030s, neither spacecraft will have sufficient power to operate any scientific instruments at all. Their transmitters will go silent. The data stream that has connected humanity to these distant explorers for nearly half a century will cease. The last signals, faint beyond anything you could imagine, will fade into the noise floor of the Deep Space Network's receivers, and then there will be nothing. After that, both Voyagers will continue drifting outward through interstellar space as inert metal artifacts. They will carry no active instruments. They will send no signals. But they will carry something else. Each spacecraft bears a golden record, a 12-inch gold-plated copper disc encoded with sounds and images selected to represent the diversity of life and culture on Earth. Greetings in 55 languages. Music from Bach to Chuck Berry. The sound of wind, rain, surf, and birdsong. Photographs of humans, animals, landscapes, and structures. These records were designed as messages to any extraterrestrial intelligence that might someday encounter the spacecraft. The probability of that encounter is, by any honest assessment, vanishingly small. Interstellar space is so incomprehensibly vast that 2 small spacecraft drifting through it without propulsion have essentially zero chance of approaching another star system within any meaningful time frame. Voyager 1 is headed in the general direction of the constellation Ophiuchus, and will pass within approximately 1.6 light-years of a star called Gliese 445 in roughly 40,000 years. It will not come close enough for gravitational capture. It will not come close enough for detection by any technology we can currently envision at that star. It will simply drift past, a tiny fleck of metal in an ocean of nothing, carrying a message that no one may ever read. This image captures something essential about the boundary these spacecraft crossed. The heliopause is not just a scientific demarcation, it is the edge of safety. On one side, the sun provides energy, magnetic protection, and a navigational anchor. On the other side, all of that vanishes. The solar wind stops, the magnetic shield drops. The familiar radiation environment is replaced by one that is constant, elevated, and inescapable. The sun itself diminishes from a life-giving furnace to a bright point of light that grows slowly fainter with every passing year, every passing decade, every passing millennium, until it is lost among the millions of other points of light that look exactly the same. Voyager 1 crossed that line at roughly 38,000 miles per hour and kept going. It did not slow down. It did not pause. There was nothing to slow it and nothing to stop for. The interstellar medium offered no resistance worth measuring and no destination worth seeking within any human-relevant time frame. The spacecraft simply continued its trajectory, moving away from the sun at the same speed it had maintained for decades, trading the familiar for the alien with no ceremony and no return. That crossing happened over a decade ago. Since then, Voyager 1 has travelled an additional distance roughly equivalent to the span between the Sun and Uranus. Yet it remains within the immediate vicinity of the heliopause in galactic terms. The nearest star is still over 4 light-years away. At its current speed, even the nearest star would require a journey measured not in centuries but in tens of thousands of years. The spacecraft has been in interstellar space for more than a decade and has traversed an almost negligible fraction of the gap to the nearest neighbouring star. This single fact illuminates the scale of what lies ahead. The heliopause was the doorway. Voyager stepped through it, and on the other side stretches a corridor so long that the doorway itself is already forgotten against the immensity of what comes next. What fills that corridor, what the interstellar medium truly is at the level of atoms and fields and radiation, is a story that defies the simplistic label of empty space and replaces it with something far stranger. There is a word that has haunted our understanding of the cosmos for centuries: empty. It shows up in textbooks, in documentaries, in the casual shorthand of even professional astronomers describing the regions between stars. The void, the vacuum, the blank darkness stretching from one sun to another. This word is not entirely wrong, but it is so catastrophically incomplete that relying on it creates a mental image of interstellar space that misses virtually everything real, everything dangerous, and everything physically consequential about the environment that fills the overwhelming majority of our galaxy. Beyond the heliopause, the region that Voyager entered and confirmed through direct measurement, there exists something. It has density, it has temperature, it has chemical identity, it has magnetic architecture and dynamic behavior that changes over timescales spanning millions of years. Scientists call it the interstellar medium, and understanding what it actually is requires letting go of nearly every assumption your brain carries about what matter should look like, how environments should behave, and what it means for a place to be full or to be barren. Start with the most fundamental physical quantity. How much matter is actually present between the stars? On the surface of Earth, at sea level, every cubic centimetre of the atmosphere surrounding you contains approximately 25 billion molecules. That number, 25 followed by 18 zeros, represents a concentration of matter so thick that molecules slam into each other billions of times per second. This density is what gives air its substance, its resistance, its ability to transmit sound and scatter sunlight into a blue sky. You can feel air against your skin. You can push against it with your hand. It is tangible. It is everywhere. Now leap to the most extreme vacuum conditions that human engineering has ever produced. In specialized laboratory chambers designed for surface science and spaceflight simulation, physicists can reduce particle counts to roughly 100,000 molecules per cubic centimetre. These are the emptiest environments ever manufactured on this planet. Nothing in human industrial or scientific capability can push emptiness further than this. 100,000 particles per cubic centimetre is our technological floor. Now consider interstellar space. In the general diffuse regions filling the volume between stars within the Milky Way, the average particle density is approximately 1 atom per cubic centimetre. 1. A solitary hydrogen atom floating in a volume the size of a sugar cube. In some regions, the density climbs modestly to 10 or perhaps 100 atoms per cubic centimetre near the edges of cold molecular clouds. In others, particularly the vast hot cavities blown open by ancient supernova explosions, the density plunges to 1/100th of an atom per cubic centimetre or even less. At those concentrations, you would need to search through 100 separate sugar cube volumes before encountering a single particle. The ratio between terrestrial atmospheric density and the typical interstellar medium is not a factor of thousands or millions. It is a factor of approximately 25 billion. The gulf is so large that no simple comparison captures it honestly. It exceeds the ratio between a single raindrop and all the water in Earth's oceans. It exceeds the ratio between a human hair's width and the distance from Earth to the Sun. It belongs to that category of numbers that exist comfortably in equations, but refuse to sit comfortably in the human mind. No metaphor captures this gulf. No human experience approximates it. The interstellar medium exists in a state of rarefaction so extreme that it challenges the very definition of the word substance. If you could somehow sweep up all the interstellar gas contained within a cube, 100 kilometers on each side, a volume roughly equivalent to a small European country stacked 100 kilometers high, the total collected material would weigh less than a few milligrams. The entire contents of that enormous region could rest on the tip of a ballpoint pen without registering on any scale you could buy. Yet this near-nothingness is not featureless. It has architecture. It has phases that coexist in a complex and dynamic relationship governed by heating, cooling, and the relentless input of energy from stellar sources throughout the galaxy. Understanding these phases is essential to grasping what the interstellar medium actually is, rather than what the word empty lazily implies. Scientists have identified several distinct states in which the interstellar gas exists, each characterized by radically different temperatures and densities, each occupying a different fraction of the galaxy's volume, and each maintained by different physical processes. The cold neutral medium is, relatively speaking, the densest stable phase of the diffuse interstellar gas. Here, particle concentrations reach 20 to 50 atoms per cubic centimetre, still preposterously thin by any earthly standard, but representing genuine concentrations relative to the surrounding medium. Temperatures in this phase hover around 80 to 100 Kelvin, approximately -170 to -190 degrees Celsius. Hydrogen atoms in these regions move sluggishly, barely drifting through space. The cold neutral medium tends to organize itself into sheets and filaments and irregular clumps distributed throughout the galactic disk. These cold structures are where star formation ultimately begins. When enough cold gas accumulates in a single gravitational well, the internal thermal pressure can no longer resist the inward pull, and the gas collapses toward the formation of new stellar systems. But this dense, cold phase occupies only a small fraction of the galaxy's interstellar volume, perhaps 2 to 4%. It is the exception within an environment that is already an exception to everyday experience. Far more volumetrically significant is the warm neutral medium. Here, temperatures rise to approximately 6,000 to 10,000 Kelvin, and densities drop to roughly 0.2 to 0.5 atoms per cubic centimetre. Hydrogen, in this phase, remains electrically neutral, each atom retaining its single electron, but the atoms move at considerably higher velocities due to the elevated thermal energy. The warm neutral medium fills an estimated 30 to 40% of the galactic disk's volume, forming the pervasive background through which colder clouds and hotter cavities are scattered. This is the phase that the Voyager spacecraft encountered after crossing the heliopause. The local interstellar cloud, the specific parcel of interstellar gas through which our solar system is currently travelling, consists primarily of warm, partially ionized gas at temperatures near 7,000 Kelvin, with a density of roughly 0.2 atoms per cubic centimetre. It is the interstellar medium's default setting in our cosmic neighbourhood. Hotter and more tenuous still is the warm ionized medium, where temperatures climb to 8,000 to 12,000 Kelvin, and ultraviolet photons from massive young stars have stripped electrons from hydrogen atoms, converting the gas into a plasma of free protons and free electrons. This ionized gas behaves fundamentally differently from its neutral counterpart. Plasma responds to magnetic fields. Its motions generate electrical currents. It emits radiation at characteristic wavelengths, particularly the red glow of hydrogen alpha emission that astronomers can detect across thousands of light years. The warm ionized medium fills roughly 20 to 25% of the galactic disk volume and produces a faint but measurable luminosity spread across the sky, tracing out the distribution of ionized gas throughout the spiral arms and above the galactic plane. But the phase that dominates the galaxy's interstellar volume in the broadest sense is also the most extreme. The hot, ionized medium consists of gas superheated to temperatures of 100,000 to 10 million Kelvin, with some regions exceeding even that staggering figure. Despite these furnace-like temperatures, the density drops to approximately 0.001 to 0.01 atoms per cubic centimetre. This superheated plasma fills enormous cavities within the interstellar medium, regions carved out by the accumulated violence of massive stellar evolution. When a star with a mass greater than roughly 8 times the Sun's mass exhausts its nuclear fuel and collapses, the result is a supernova, an explosion that releases approximately 10 to the 44 joules of kinetic energy into the surrounding interstellar gas. For perspective, this single event liberates roughly as much energy as the Sun will produce over its entire 10 billion year lifetime. The blast wave from the supernova races outward at thousands of kilometers per second, sweeping up interstellar gas like a snowplow, compressing it into a thin, expanding shell and leaving behind an interior cavity of extremely hot, extremely diffuse plasma. These supernova remnants can grow to span dozens of light years in diameter before their expansion stalls, and the hot gas gradually begins to cool and blend back into the ambient medium. In regions where massive stars cluster together, as they frequently do in stellar associations and giant molecular cloud complexes, the combined effects of stellar winds and sequential supernova explosions produce structures on an even grander scale. Superbubbles, as these are called, can extend across several hundred light years and remain at extreme temperatures for millions of years, continuously reinflated by fresh energy input from the ongoing deaths of massive stars within them. Some models suggest these superbubbles interconnect, forming a network of hot tunnels threading through the galactic disk and creating a pervasive substrate of superheated plasma that accounts for 50 to 70% of the total interstellar volume. Our own solar system resides within one such structure, the local bubble, a region of anomalously low density and elevated temperature, roughly 300 light-years across, that was excavated by a series of supernovae occurring over the past 10 to 20 million years. The temperature structure of the interstellar medium creates one of its most profoundly counterintuitive features. A region at 10 million Kelvin sounds like it should incinerate anything it touches. In terrestrial experience, temperature means heat, means danger, means destruction. Place any object in a 10 million degree environment on Earth and it will be vaporized in a fraction of a second. But temperature in physics measures the average kinetic energy of individual particles, not the total thermal energy delivered to a surface per unit time. When those particles are separated by meters or kilometers, the rate at which they actually strike a surface drops to negligible levels. A spacecraft immersed in the hot, ionized medium would not be heated by its environment. Individual particles would occasionally strike the hull at extraordinary velocities, each one delivering a minuscule amount of energy. But the interval between impacts would be so long, and the energy per impact so small relative to the spacecraft's total thermal budget, that the net effect would be imperceptible. Meanwhile, the spacecraft would radiate its own thermal energy into the surrounding vacuum as infrared photons, losing heat faster than the sparse plasma could replace it. The effective experience would be one of relentless, inescapable cold. In interstellar space, million-degree temperatures and functional freezing coexist in the same cubic meter. The physics is real. The experience is the opposite of what the numbers seem to promise. Woven through every phase of the interstellar medium, connecting them and shaping their behavior at every scale, is a component that receives far less public attention than it deserves: the galactic magnetic field. This field does not originate from a single source. Earth's magnetic field is generated by convective currents in the planet's liquid iron core, a compact dynamo with a well-defined center. The galactic magnetic field arises instead from the collective motions of charged particles throughout the interstellar medium, amplified and sustained by the differential rotation of the Milky Way. The inner regions of the galaxy orbit the galactic center faster than the outer regions. This shearing motion stretches and twists magnetic field lines, continuously regenerating the large-scale field against the natural tendency of turbulence and resistive dissipation to destroy it. The strength of the resulting field is modest. In the general diffuse interstellar medium, measurements indicate typical field strengths of 1 to 5 microgauss. Earth's surface magnetic field, by comparison, measures approximately 500 milligauss. The galactic field is roughly 100,000 to 500,000 times weaker than the field that deflects your compass needle. A common kitchen magnet produces a field millions of times stronger, but the galactic magnetic field extends across light years. It threads through the spiral arms, curves along the disk, loops into the halo above and below the galactic plane. Over distances of parsecs and kiloparsecs, a field measured in microgauss accumulates enormous influence on the behavior of charged particles, the dynamics of gas clouds, and the propagation of one of the most important features of interstellar space, a feature that bears directly on the question of what it would mean to exist beyond the heliosphere. Cosmic rays. These are not electromagnetic rays. The name is a historical artifact from the early 20th century, when the nature of the radiation was still unknown. Cosmic rays are particles, primarily protons, constituting roughly 87% of the total flux, with helium nuclei making up about 12% and heavier ions comprising the remainder. A smaller population of cosmic ray electrons accompanies the nuclear component. These particles have been accelerated to extraordinary energies by astrophysical shock waves, predominantly those generated by supernova explosions rippling through the interstellar medium. The acceleration mechanism is elegant and violent. When a supernova blast wave expands outward, it creates a shock front, a thin boundary where the gas velocity drops abruptly from supersonic to subsonic. Charged particles near this shock front can bounce back and forth across the boundary, gaining energy with each crossing through a process called diffusive shock acceleration. The particle approaches the shock, is deflected by turbulent magnetic fields on one side, crosses the shock, is deflected again on the other side, recrosses, and gains energy at each transit. Over thousands of years of repeated crossings, individual protons can reach energies exceeding 10 to the 15 electron volts, far beyond what any human-built particle accelerator achieves. Once launched into the interstellar medium, these energetic particles begin a long and tortuous journey through the galaxy. They do not travel in straight lines. The galactic magnetic field bends their trajectories, causing them to spiral along field lines, with radii determined by their energy and the local field strength. Lower energy cosmic rays spiral tightly and are strongly affected by magnetic irregularities. Higher energy particles spiral more broadly and are deflected less, but all are scattered by the turbulent magnetic structures that permeate the interstellar medium, randomizing their directions over time. The result of this scattering is that cosmic rays, having originated from point sources like individual supernova remnants, are thoroughly mixed throughout the galaxy within tens of millions of years. They arrive at any given location from essentially all directions simultaneously. Their angular distribution is isotropic to a remarkable degree. You cannot point at a cosmic ray and trace it back to its source, because its path has been scrambled beyond recovery by millions of years of magnetic deflections. The energy spectrum of cosmic rays spans a breathtaking range. At the low end, particles carry energies of a few 100 million electron volts, comparable to protons in a medical cyclotron. At the high end, ultra-high energy cosmic rays exceed 10 to the 20 electron volts, carrying as much kinetic energy in a single proton as a baseball thrown at 60 miles per hour. The flux drops steeply with increasing energy. Low and moderate energy cosmic rays are relatively abundant. The extreme events are extraordinarily rare, but even the moderate energy population, arriving continuously from all directions, represents a steady, unrelenting radiation environment that has no equivalent inside the heliosphere. This is because the heliosphere, as established in the previous part of this story, actively deflects a substantial fraction of incoming galactic cosmic rays. The solar magnetic field and the outward pressure of the solar wind create a barrier that lower energy cosmic rays cannot easily penetrate. During periods of high solar activity, this shielding is enhanced. During solar minimum, it weakens but does not disappear. The effect is measurable and significant. Inside the heliosphere, the cosmic ray flux at Earth is reduced by roughly 30 to 50% relative to the unshielded interstellar value. Beyond the heliopause, that shielding vanishes completely. Both Voyager spacecraft recorded the transition directly. Upon entering interstellar space, each probe measured a sharp and sustained increase in cosmic ray intensity to a stable plateau that has not varied meaningfully since. The galactic cosmic ray flux in the nearby interstellar medium is constant, isotropic, and permanent. It does not cycle, it does not pulse. It simply is, a steady rain of high-energy particles arriving from every direction at every moment, with no shelter from any star's magnetic output to moderate it. When these particles encounter matter, the results are destructive at the atomic level, and the destruction unfolds through a sequence that is worth understanding in detail because it reveals why shielding against cosmic rays is so fundamentally different from shielding against any other hazard humans have ever faced. Consider a single cosmic ray ion nucleus, a relatively common component of the heavy ion flux, travelling at 95% of the speed of light. This particle is an atom of iron stripped of all 26 of its electrons, a bare nucleus carrying a substantial positive charge and moving with kinetic energy that can exceed 10 billion electron volts. It approaches a spacecraft hull made of aluminum. The moment the iron nucleus enters the aluminum, it begins interacting with the electron clouds of the aluminum atoms it passes through. Its enormous charge and velocity strip electrons from atom after atom along its path, depositing energy in a dense, narrow track. This process, called ionization energy loss, heats the material along the track to extreme temperatures at the molecular scale. In biological tissue, this ionization trail is devastating. It shatters molecular bonds along a corridor only nanometers wide but potentially centimeters long, producing a streak of chemical destruction that cellular repair mechanisms struggle to fix because the damage is so concentrated and so extensive along a single line. But the ionization trail is only the beginning. As the iron nucleus penetrates deeper into the material, the probability increases that it will strike an aluminum nucleus directly. When this happens, the collision is catastrophic for both particles. The aluminum nucleus, containing 27 nucleons, cannot absorb the impact of a relativistic iron nucleus containing 56 nucleons. Both nuclei shatter in a process called spallation. The fragments include free protons, free neutrons, lighter nuclei such as helium, lithium, and beryllium, and unstable particles called pions. The pions decay almost immediately into gamma rays and other particles, producing a burst of electromagnetic radiation at the impact site. The neutrons, carrying no electrical charge, fly outward through the surrounding material without being deflected by electron clouds, penetrating far deeper than charged particles can. These secondary neutrons are particularly dangerous because they interact with other nuclei along their paths, occasionally triggering additional spallation events and creating a branching tree of tertiary particles. The result is called a hadronic cascade. A single incoming iron nucleus can produce hundreds of secondary particles within the first few centimeters of material, and those secondaries can produce hundreds more as they interact with the surrounding atoms. The cascade fans outward and downward through the shielding like a shower, converting one extremely energetic particle into a spray of lower energy particles spread across a wider volume. Some of these secondary particles are more biologically damaging per unit of energy than the original cosmic ray, because they deposit their energy in patterns that are especially difficult for living cells to repair. This is why adding mass to a spacecraft hull does not straightforwardly solve the radiation problem. For lower energy cosmic rays, shielding works as intuition suggests. The material absorbs the particle and the threat is eliminated. But for the high-energy heavy ions that dominate the biological risk in the galactic cosmic ray flux, thicker shielding can actually increase the total radiation dose experienced on the interior side of the hull. The incoming particle is stopped, but the cascade it generates delivers a more diffuse, and in some respects more harmful radiation field to anything sheltering behind the shield. Optimal shielding strategies involve materials rich in hydrogen, such as water or polyethylene, which produce fewer heavy secondary fragments when struck by cosmic rays. But even these materials provide diminishing returns beyond a certain thickness, and the mass penalty of carrying sufficient shielding for a decades-long voyage adds enormously to the propulsion and energy requirements that already strain the boundaries of the possible. There is one more component of the interstellar medium that deserves attention, not because it dominates by mass or volume, but because its effects are disproportionate to its minuscule abundance: interstellar dust. These are not the dust motes visible in a beam of sunlight. Interstellar dust grains are microscopic solid particles, typically measuring between a few nanometers and a few tenths of a micrometer in diameter. Smaller than a wavelength of visible light, they are composed primarily of silicate minerals and carbonaceous compounds, essentially tiny fragments of rock and soot. Their origin lies in the outer atmospheres of evolved stars, particularly red giants and asymptotic giant branch stars, where conditions of temperature and density allow solid particles to condense from cooling stellar outflows. Supernova explosions also produce and distribute dust, seeding the interstellar medium with freshly forged solid material. The number density of interstellar dust is almost absurdly low. In the diffuse interstellar medium, a typical figure is roughly 1 grain per 100,000 cubic meters, one microscopic speck drifting alone in a volume the size of a large residential building. Yet these vanishingly sparse particles produce effects that shape the observational history of astronomy and the chemical evolution of the galaxy. Dust absorbs and scatters visible light. This property is responsible for the dark lanes and rifts visible in images of the Milky Way. The prominent dark band splitting the glowing arch of our galaxy's disk as seen from Earth is not a gap in the distribution of stars. It is a curtain of interstellar dust lying between us and the billions of stars beyond, absorbing their visible photons and re-radiating the energy at infrared wavelengths invisible to the human eye. For over a century, this extinction of starlight by dust confused astronomers, leading them to underestimate galactic distances and misinterpret the structure of the Milky Way. Only with the development of infrared and radio astronomy, wavelengths to which dust is largely transparent, could scientists see through the veil and map the galaxy's true structure. Dust also serves as the galaxy's chemical workshop. In the incredibly sparse conditions of interstellar space, atoms drifting through the gas phase encounter each other so rarely that chemical reactions between them proceed at negligible rates. Two hydrogen atoms passing within reactive distance of each other in the diffuse medium might wait millions of years for the encounter to happen. But when an atom lands on the surface of a dust grain, it can stick, migrate across the surface, and encounter other adsorbed atoms with which it can react. The grain surface acts as a meeting place and a catalyst, dramatically accelerating reactions that would be impossibly slow in the gas phase alone. The most important of these grain surface reactions is the formation of molecular hydrogen. Two hydrogen atoms adsorbed on a dust grain surface can combine into a molecule of H2, which then desorbs back into the gas. This process is the primary pathway by which molecular hydrogen forms in the interstellar medium. Without dust grains facilitating this reaction, the galaxy's supply of molecular hydrogen, the essential fuel for gravitational collapse and star formation, would be drastically lower. Dust grains, despite their almost unimaginable scarcity, are indispensable to the galaxy's ability to form new stars. The chemical inventory of interstellar space extends well beyond molecular hydrogen. As of the mid-2020s, astronomers have identified over 270 distinct molecular species in interstellar and circumstellar environments. Simple diatomics like carbon monoxide and hydroxyl radical are common in many phases of the medium. More complex molecules, including formaldehyde, methanol, acetaldehyde, and even amino acid precursors like glycine, have been detected in cold, dense molecular clouds, where temperatures drop below 20 Kelvin and densities climb above several thousand particles per cubic centimeter. Polycyclic aromatic hydrocarbons, large carbon ring structures, appear to be ubiquitous throughout the diffuse medium, producing characteristic infrared emission features that astronomers detect across the galaxy and beyond. This molecular richness is concentrated overwhelmingly in the cold, dense phase. In the warm and hot phases that fill most of the interstellar volume, ultraviolet radiation from nearby and distant stars dissociates molecular bonds within timescales of a few 100,000 years. Only the hardiest molecules persist in exposed diffuse conditions, primarily carbon monoxide, which is shielded by its own abundance through a process called self-shielding, and molecular hydrogen in regions where even modest dust columns provide protection from photodissociation. The general diffuse interstellar medium between stars is chemically sparse, a thin broth of atoms and atomic ions with occasional molecular survivors and scattered microscopic dust grains. This, then, is what fills the space between stars, not nothing, not the featureless void of popular imagination. It is a dynamic, layered, magnetically threaded, radiation-saturated, chemically active medium with temperature extremes spanning 5 orders of magnitude.